Note that today the committee is meeting virtually, and therefore I want to announce a couple of reminders to the members about the conduct of this hearing. First, please keep your video feed on as long as you are present in the hearing. Even if you need to go get a peanut butter and jelly sandwich, just leave the video on and come back. Members are responsible for their own microphones. Also, please keep your mic muted unless you're speaking. And finally, if members have documents that they wish to submit for the record, please email them to the committee clerk, whose emailing address was circulated prior to the hearing. So good morning, welcome to our witnesses. Thank you for being here. On February 18th, just a few months ago, millions of people waited as the Mars Perseverance rover dove through the Martian atmosphere at speeds of 12,000 miles per hour and implemented a complex sequence of operations leading to the rover's safe landing in Jezero crater. The cheers upon confirmation of the rover's successful arrival lifted us as a nation after a year that had tried us like no other. I just want to take a minute to celebrate and thank the people who got us to this point. Completing development, assembly, launch, and then landing, all while navigating the challenge of the COVID-19 pandemic, is a shining example of the tireless dedication of the NASA Jet Propulsion Laboratory and partner teams. So I want to thank them all for embracing the spirit of perseverance. And speaking of the name Perseverance, I want to give a plug to Alexander Mather, a middle student from Burke, Virginia, who won the naming contest for the Mars 2020 rover with the very apropos name Perseverance. Today, we pivot our attention from launch and landing to science and discovery. Joining us here today are a group of experts who, no doubt, will whet our appetites for science as Perseverance prepares to explore the remains of an ancient lake and delta in Jezero crater and search for signs of past life. Perseverance's work isn't the beginning of a scientific journey. It's a continuation of NASA's systematic robotic exploration of the red planet that started over 50 years ago with the Mariner flybys in the 1960s and the Viking landers in the 1970s. And I still remember so clearly those photos. Perseverance is now the 5th U.S. rover and 9th U.S. landing spacecraft to carry out science operations on Mars, achievements that to date only the United States can claim. But next month, China will attempt its first landing of a spacecraft that will descend from the Tianwen-1 spacecraft orbiting Mars. NASA spacecraft and others from the United Arab Emirates, India, and Europe are also in orbit around Mars. But make no mistake, Perseverance is a first. It's seeking what some might consider the holy grail of NASA, of Mars science, samples that will be collected, stored, and returned by a future mission to Earth for a scientific analysis. A 2007 National Academies report recommended that the highest priority science objective for Mars exploration must be the analysis of a diverse suite of appropriate samples returned from carefully selected regions on Mars. And in 2011, the National Academies recommended the first step in a Mars sample return campaign as the highest priority large-scale planetary science mission. Perseverance's instruments and the samples it will collect will allow scientists to trace the evolution of Martian climate, geography, and the nature and complexity of any detected organic material. Martial samples could also tell us more about our own place in the universe and our own very being. Scientists tell us that when stars exploded in death, they dispersed new elements throughout the universe, elements including carbon, oxygen, nitrogen, which happen to comprise our own makeup. And that explains that we're made of this very stardust. Will Perseverance give us the opportunity to see images of our elemental selves in Martian dirt? Armed with multiple cameras and 7 sophisticated science instruments, Perseverance is about to begin the return on the years of hard work and investment in the nation's most advanced Mars rover to date. That return is sure to bring scientific discoveries about Mars, its habitability for past life, insights and knowledge to help us prepare for sending humans there, and the inspiration that propels our nation to dream big, and our scientists, engineers, mathematicians, and future explorers to embrace ambitious challenges. I have to confess that one of my favorite books is the Red Mars, Blue Mars, Green Mars series from Kim Stanley Robertson, and would recommend anybody watching in the hearing or on C-SPAN 3 to go buy it and read it right away. And I hope that our witnesses will continue to give us hope about the future of the human beings on Mars. So I look forward to our witness testimony, and I now recognize my friend and the ranking member of the Space Subcommittee, Dr. Brian Babin in Texas. Dr. Babin.
Yes, sir. Thank you, Mr. Chairman, and thank all these great witnesses that we're about to hear. NASA's planetary science missions exemplify the American spirit of exploration. They continue our very long tradition of our nation of discovery and scientific inquiry. Missions like Perseverance expand humanity's reach throughout the solar system, inspire the next generation of explorers, and maintain technological expertise that is so important to our nation's economic and national security. Our nation once again experienced a collective 7 minutes of terror as the Perseverance rover descended to the Martian surface 2 months ago. It will continue our long history of searching for evidence of past life, produce oxygen on the Martian surface, and has also demonstrated the very first controlled flight on another planet with our helicopter Ingenuity. Perseverance builds on the success of the Curiosity rover that landed on Mars nearly a decade ago, and the Spirit and Opportunity rover's landings in 2004, not to mention the 1976 Viking landing, the 1997 Pathfinder landing, and the Sojourner rover, and the more recent Phoenix and Insight landing. The landers were also enabled by spacecraft like Mariner, Mars Global Surveyor, Mars Odyssey, Mars Reconnaissance Orbiter, and the MAVEN spacecraft. So far, the United States is the only nation to successfully land and operate on the red planet. To be more specific, the Jet Propulsion Laboratory is the only entity to do so successfully. Other nations have tried, and the Soviet Union has even landed, but no other nation has landed and operated for more than a few seconds. But even we have experienced failures. With all of our success, it is easy to forget that landing on Mars is a very hard task. We were reminded of this in the 1990s with the loss of the Mars Observer, the Mars Climate Orbiter, and the Mars Polar Lander. Despite these losses, we remain undeterred. Going forward, other nations continue to explore Mars. Europe and Russia still operate the trace gas orbiter around Mars. India's Mars Orbiter mission entered Mars orbit in 2014, and the United Arab Emirates HOPE mission and China's Orbiter and Rover entered Mars orbit in February. We also expect another Russian and European ExoMars mission and a Japanese Mars Moon exploration mission in a couple of years. Mars is getting busy and crowded, and for lots of reasons. Other nations see the benefit of planetary exploration and Mars exploration in particular. Aside from the technological advantages of Mars exploration, some nations, particularly China, see this as a way to legitimize the Communist Party's leadership. Debates about prohibitions on cooperation with China are also coming to light as China prepares to land its own rover on Mars. Cooperation is always a tricky subject when it comes to space, and Mars is no different. The Obama administration canceled the ExoMars partnership with Europe because of cost overruns with the James Webb Space Telescope. That pushed Europe to partner up with Russia for that mission. As Mars exploration becomes increasingly international, Congress and the administration will have to carefully weigh the pros and cons of partnerships and the impact of those partnerships on technology transfer and theft, national security, human rights, and Communist Party legitimacy. It is a privilege to partner with the world leader in exploration, and they might have more to gain from partnering with us than we do with them. I look forward to many more exciting discoveries as we embark on a future planetary mission to Mars, like the bold sample return mission. NASA's planetary science program balances a vast portfolio of missions from large, medium, and small sizes and explores all of our solar system, including the outer planets, asteroids, and hopefully even a return to Venus in the future. I also look very much forward to understanding how big ticket items like the Mars Sample Return mission, the Europa Clipper mission, reconstituting the Nancy Grace Roman telescope under the Astronomy Division, and significantly expanding the Earth Science Division, and how it will impact the agency and other programs. thank you very much for our witnesses for appearing today. And I look forward to your fascinating testimony. So with that, I'll yield back, Mr. Chairman.
Mr. Babin, thank you very much. And with that, I now recognize the ranking member of the full committee, Mr. Lucas, for an opening statement.
Thank you for holding this hearing, Mr. Chairman. When NASA's Perseverance rover landed on Mars in February, it became the 8th craft to successfully land on the Martian surface in a little over 40 years. Every one of these vehicles were American-made, and each of these explorers built on the technology and scientific knowledge gained from the craft which came before it.
I can't hear anything.
Perseverance.
Can anybody hear me?
Ambitious mission continues this legacy of innovation. The vehicle is searching for signs of ancient life as we speak, and it's helping us gain a better scientific understanding of the red planet. In addition to its scientific mission, Perseverance is helping us demonstrate new technologies, which will help aid future exploration of other planetary bodies, both through robotic and human missions. A few weeks ago, we saw the launch of a small helicopter named Ingenuity, which made the first powered flight on another planetary body, which has now made 3 more flights, each lasting longer and traveling greater distances. In addition, Perseverance includes a technology demonstration called MOXIE. The instrument's purpose is to take the Martian atmosphere, which is mostly carbon dioxide, and create breathable air. The first demonstration was successful, producing more than 10 minutes of breathable air for an astronaut. Later, Perseverance will collect several samples of Martian soil, which will be left on the Martian surface. These samples will eventually be retrieved by a future mission and returned to Earth for research. There are many other cutting edge and inspiring facets to Perseverance, each of which are laying the groundwork for future crewed exploration of Mars. Though the U.S. has demonstrated unique leadership in Martian exploration, we're not the only ones interested in exploring the solar system. In the weeks leading up to Perseverance's landing, a craft managed by the United Arab Emirates entered orbit. Additionally, another craft made by China entered orbit, the first vehicle from that country to do so. In the coming months, China will attempt to be the second country to join the U.S. in successfully landing a rover on Mars. This comes little more than 2 years after China first successfully landed a craft on the far side of the moon, and only months after China became the second country to successfully return samples of lunar surface to the Earth. Less than 12 hours ago, China launched the first module of a new space station, which it hopes to have completed by the end of next year. With these recent moves, the Chinese Communist Party has all but declared its intent to challenge U.S. leadership in space. These recent examples serve as stark reminders of why we need to avoid complacency in our space program. We must be mindful of this as our committee considers how best to increase investments in basic research and develop a new generation of STEM participants. We have seen repeatedly the power of NASA's missions to inspire future generations. I was pleased by the Biden administration's public support for the continuation of the Artemis program, which will return American astronauts to the lunar surface this decade and lay the groundwork for future human exploration of Mars. Now, Congress must do our part and ensure that NASA has the resources and the direction it needs to execute this mission. I want to thank our witnesses for being here today and sharing their experiences working on this inspiring mission. I look forward to hearing ways this committee can continue to inspire future generations. Thank you, and I yield back my time, Mr. Chairman.
Thank you, Mr. Lucas, very much. If there are other members who wish to submit additional opening statements, your statements will be added to the record at this point. Let me now move to our witness introductions. Our first witness is Dr. Michael Meyer. And Dr. Meyer is a senior scientist at NASA headquarters in the Science Mission Directorate and is the lead scientist for NASA's Mars exploration and for the Mars sample return programs. He also serves as the program scientist for the Mars Science Laboratory Curiosity mission. During his career at NASA, Dr. Myers held many roles focused on the study of life in the universe, including as a senior scientist for astrobiology. His primary research interest is in microorganisms living in extreme environments, particularly the physical factors controlling microbial growth and survival. Dr. Meyer received his Bachelor of Science degree in biology from Rensselaer Polytechnic Institute and a Master of Science and a doctorate in oceanography from Texas A&M University. Welcome, Dr. Meyer. And we will cycle back to you in just a minute. I'm going to introduce the others, and then we'll start with you, Dr. Meyer. Our second witness is Dr. Bethany Ellman, Professor of Planetary Science and Associate Director of the Keck Institute for Space Studies at Caltech. Dr. Ellman is co-investigator on the MASCOM-Z and the SHERLOC instrument teams for the Mars 2020 Perseverance rover. She was also a member of the science team for the Spirit and Opportunity Mars exploration rovers and an affiliate of the Dawn orbiter team during its exploration of the largest asteroid and dwarf planet series. Dr. Ellman's research focuses on the mineralogy and chemistry of planetary surfaces, remote sensing techniques and instruments, astrobiology, and science policy and outreach. Her primary focus is on unraveling Mars's environmental history and understanding water in the solar system. Dr. Ehlmann received her undergraduate degree from Washington University in St. Louis, a Master of Science and a doctorate in Geological Sciences as a National Science Foundation Graduate Fellow at Brown University. So welcome, Dr. Ehlmann. Our third witness is Dr. Luther Beagle, Principal Investigator of the Mars Perseverance Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals, SHERLOC, instrument at the Jet Propulsion Laboratory. As a principal scientist at the Jet Propulsion Laboratory, Dr. Beagle is responsible for conducting NASA-funded research as a PI and co-I in planetary science, focusing on detection and characterization of organic molecules for the identification of potential biosignatures. Dr. Beagle received a Bachelor of Science in Physics and Astronomy from the University of Delaware and a Master of Science in Physics and a doctorate in Astrophysics from the University of Alabama at Birmingham. So welcome, Dr. Beagle. I'm sure our president will be pleased to know we have a University of Delaware graduate here. And our final witness is Dr. Tanja Bosak, a professor of geobiology at the Massachusetts Institute of Technology and return sample science co-lead of the Mars 2020 Perseverance rover. Dr. Bosak's research focuses on how microbial processes leave chemical, mineral, and morphological signals in sedimentary rock. Her lab uses research approach to explore modern geochemical and sedimentological processes, interpret the coevolution of life and the environment during the first 80% of Earth's history, and look for signs of past life on Mars. Dr. Bozak received her undergraduate degree in geophysics from the Zagreb University and a doctorate in geobiology from the California Institute of Technology. So welcome, Dr. Bozak. So we will start with Dr. Meyer, and you each have 5 minutes. Dr. Meyer, floor is yours.
Thank you. Chairman Beyer, Ranking Member Babin, and members of the subcommittee. I am honored to appear before the subcommittee to discuss Mars science and the role of the Perseverance rover plays in NASA's broader Mars exploration program. Mars has captured the public's imagination as the planet in our solar system most similar to Earth. Both planets formed 4.5 billion years ago and are the only planets to have known to be able to support life. Nevertheless, this transformation over time to the present has followed dramatically different paths. By studying Mars, we can learn about our history as well. NASA's Mars exploration program studies Mars as a planetary system in order to understand its extreme climate variation on different timescales, its history of geological processes that have shaped Mars through time, its potential to have hosted life, and its future exploration by humans. As we learned about Mars, the strategy has evolved from follow the water to explore habitability to seek the signs of life, and has brought us to the threshold of sample return with the Perseverance mission. Perseverance is the most sophisticated rover ever to have been sent to the Red Planet, with a name that embodies NASA's passion and our nation's capability to take on and overcome challenges. As such, Perseverance will contribute to all 4 of NASA's high-level goals of Mars during this exploration. In addition, Perseverance will collect and carefully select rock and regolith samples for future return to Earth. Perseverance has already achieved at least 5 firsts. Terrain relative navigation enabled the descending spacecraft to avoid hazards. Perseverance landed in a place too dangerous for previous missions to land, but with terrain relative navigation, we could and we did. The helicopter Ingenuity was the first aircraft in history to make a power-controlled flight on another planet, a true Wright brothers moment. SuperCam captured the sounds of Martian wind and the first audio of laser zaps on another planet. The Mars Oxygen and in situ resource utilization experiment has extracted 99% pure oxygen out of the Martian atmosphere, a resource for future rockets and humans. And Perseverance is the first leg of a round trip to Mars by caching samples on the surface. All of us get to ride with Perseverance. The Perseverance mission carries more cameras than any interplanetary mission in history. This has allowed NASA to watch its own mission land on another world and for the public to share in the experience. We have accomplished much and will continue to do so because of the Mars exploration program. NASA's InSight mission will spend its extended mission listening for more Mars earthquakes. NASA's other rover, Curiosity, continues to make exciting discoveries during the climb up Mount Sharp, just now entering the Sulfay unit, which is a window into the Mars history when the planet became cold and dry. NASA is also studying Mars from orbit with the Mars Reconnaissance Orbiter, MAVEN, Odyssey, with ESA's Mars Express missions, expanding our understanding of the dynamic planet we see today. For example, the science community has been able to piece together the anatomy of a 2018 global dust storm, the storm that ended NASA's Opportunity mission. We now understand the probability and the progression of global dust storms and their effects, thereby reducing the risks of future missions. As the program has brought us to the sample return, this will be the first time samples will be brought back from another planet. It involves 3 missions and a close collaboration with the European Space Agency. Once back on Earth, we can analyze the samples in ways we can't on Mars. We can use instruments too large and too complex to send to Mars, and we can save material for future generations, using instruments that have not yet been invented and addressing questions that no one has yet thought of. NASA's Mars exploration program continues to lead the world in learning about Mars and developing a technology that allows us to delve deeper into the secrets of the red planet, making significant progress in its goals of searching for life, understanding Mars climate, understanding Mars geology, and preparing for human exploration. I want to thank Congress for their steady and generous support of Mars science, and I would be happy to answer any questions that you may have. Thank you.
Thank you, Dr. Meyer, very much. I promise you, we're all very excited about Mars science. Now let me introduce Dr. Bethany Ellman for her testimony.
Thank you, Chairman Meyer, Ranking Member Babin, members of the subcommittee. I appreciate all of your work to support science and exploration, and thank you for the opportunity to appear today. Our team was thrilled February 18th when JPL delivered our 1-ton rover to the surface of Mars. I'm going to focus on the big picture science questions answerable at Mars and how we conduct our exploration, while my colleagues will discuss the instruments and sample return portions. For me, and I think for many of us, there is just a DNA of exploration in us as humans. We're drawn to ask profound questions. Are planets like our Earth rare, or are they common? Is there life elsewhere in the universe? One of the reasons I study Mars among all solar system planets is that Mars is a linchpin to answering these questions. The different fates of our Earth-like worlds in our solar system are recorded on Earth, Venus, and Mars. But what's special about Mars is that there's a vast rock record that spans the interactions of the interior of the planet, the atmosphere, the climate, that record what makes a planet habitable over its first billion years. I draw the subcommittee's attention to the Mars Architecture Strategy Working Group report from November that goes far more deeply than I can in 5 minutes on these questions, reviewing the findings of our program, reaffirming the priority of sample return, and identifying how to move forward in the next decade about the interaction between science, scientific exploration, human exploration in the growing commercial space sector, because as was mentioned, it's an exciting time right now at Mars, 11 operating spacecraft from 5 different agencies. So what does Perseverance do? Perseverance is both a science mission like past rovers, and it's the first step in an ambitious 3-mission sequence to return samples to Earth. We've already accomplished a number of our technology goals, but what remains is to study the region's history, climate, look for signs of life. We act as a robot geologist, but I now want to move to my slides that I have, because we have a wealth of data from the Mars exploration program. And if we go ahead and move on to the first time step, I can talk about why this is important and what we have learned and what we will learn. What I'm showing here is a hillshade topography map of Mars, because Mars today is a cold, dry desert like the Antarctic dry valleys. 2 decades of exploration, though, have discovered thousands of outcrops of rock across the surface. Everywhere you see a colored dot on this image, it's a mineral that formed in the presence of water. Some clay minerals, like you form it in soils, some from aquifers underground, some salts. Now, there are thousands of places to explore, but we have gotten to a handful of them so far. You can see the Perseverance rover site is in a concentration of these exciting rock outcrops west of the Isidis Basin. If we zoom into where we have chosen to go with this Mars 2020 rover on the next slide, what we see here is a beautiful 45-kilometer Jezero crater. I hope if you look to particularly to the left of Jezero crater, what's exciting is that there is a landscape of 4 billion-year-old rocks. Particularly in the lower left, you can see a series of rock mesas and outcrops planing off the historical record of Mars conveniently for us to drive through. And indeed, the white dot is where we are right now on Mars. The white line is a notional traverse that we hope to undertake over the next 2 years. In Jezero crater, you can see it's a bit special. Over to the east, there's an outflow channel. That's where water once drained out. To the north and to the west, there's an inflow channel that once drained in, and this is where Jezero crater once had a lake. If we zoom in to the west, you can see this beautiful delta landform. Here I'm showing false color infrared data from one of the orbiters, the Mars Reconnaissance Orbiter in our exploration program. The yellows and the purples are volcanic formed minerals. The greens are clay and carbonate. Clay and carbonate rocks, water formed. If you were on Earth, you would go to them to find the fossils. If we go to the next slide, it highlights, just the amazing Mars coordinated exploration program, snapping our descent to the surface with the HiRISE instrument, seeing Perseverance land at this landform that we worked for 20 years to find as the target of our exploration. I'll end with the final graphic, which is hot off the presses from the MAST-CAM-Z instrument, and really, I hope, reveals the tantalizing detail of what's to come. You can see the sands and the rocks of our landing site, the distant crater rim 10 kilometers away that we will eventually climb out on, but not before exploring these sediments and deposits ahead of us. So it's a rubbly landscape, and we've got to just make the first decisions about how to drive through it. But as we finish off here, you see the mesas of the delta coming into view, those rocks that record the history of the lake. We're going to drive up to them with our instruments, sample them to select the best ones to bring back to Earth. So I look forward to reporting on our findings in the years to come.
Dr. Ellman, thank you very much. It does look like mountains I would like to climb. Dr. Beagle, the floor is yours.
Chairman Meyer, Ranking Member Babin, and members of the subcommittee, I'm honored to appear before this subcommittee on behalf of the California Institute of Technology to discuss the Mars Perseverance mission. On February 18th, 2021, the Perseverance touched down in Mars Jezero crater. As we just saw, roughly about 3.5 billion years ago, Jezero crater was the site of an ancient lake. Orbital images show that Perseverance has landed, in fact, right in front of what was once a river delta. Places like this can concentrate biologic activity and are known to be excellent sources of preservation of organic molecules. We have high hopes for this location, what this location may hold for science. All evidence points to Mars being more Earth-like in its early history, with rivers, lakes, and a large ocean potentially filling this northern hemisphere. At roughly the same time of life was starting on the Earth, water also flowed across the surface of Mars. We believe that many of these same conditions we think would be required for life on Earth were present on Mars at this time, including chemical energy sources and access to organic carbon. On Earth, many things have changed since life began a billion years ago. Key clues to the origin of life on our planet have largely been erased by weathering, erosion, and plate tectonics. On Mars, by contrast, there's little evidence of plate tectonics, and the surface has been less affected by these other processes. Thus, Mars has a much better preserved ancient rock record. Rocks on Mars could preserve key evidence of planetary formation, clues to its habitability, and potentially signs of microscopic life. Perseverance's payload has 7 instruments that will analyze samples for future return to Earth. I am the principal investigator for an instrument called SHERLOC, which stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. SHERLOC was developed to search for clues with an astrobiology relevant mission, a relevant environment on Mars. Starting soon, SHERLOC will work to identify habitable environments and see what we can do regarding Martian history. SHERLOC enables sensitive detection, characterization, and spatially resolved correlation of trace organic minerals and material within Martian outcrops. SHERLOC can identify potential biosignatures in the Martian surface and near subsurface. It does this by combining microscopic imaging and Raman and fluorescence spectroscopy to map a postage-sized stamp of a Martian sample. 2 microscopic cameras, the autofocus and contextual imager, or ACI, and the wide-angle topographic sensor for operations and engineering, or Watson, obtain high-resolution images of the surface to identify textures and features smaller than 30 microns. The Martian surface is an inhospitable place for most organic molecules due to high ultraviolet radiation and oxidizing conditions. Perseverance has an abrasion tool to get to the protected interior of rocks where organic molecules have been shown by NASA's Mars Science Laboratory, or Curiosity, to exist. Organic molecules that SHERLOC can identify are found in life as we know it, but a number of these have also been found in meteorites or known to be created through abiotic chemical processes on the Earth. This is why we call any findings by SHERLOC potential biosignatures rather than claiming to have an instrument capable of unambiguous life detection. Minerals can also be a form of biosignature. Biology can create distinctive signatures that can be observed in assemblages of astrobiology relevant materials. The presence of such assemblages in minerals in association with organics can be an important component in evaluating whether something may have been produced or brought about through biologic processes. SHERLOC will be looking for these type of features. The Mars 2020 mission is designed to collect well-characterized samples that have high scientific value. When these samples are eventually returned to Earth, they will be analyzed by state-of-the-art instruments, some which cannot be flown to Mars for a variety of reasons. Some of these instruments have not even yet been invented. The combination of knowing where a sample came from and multiple lines of evidence within that sample should be able to get us closer to answering the tantalizing question of whether life existed or exists on the next planet out from the sun. Finally, I have given many talks at schools focusing on the Mars 2020 mission and SHERLOC in particular. I usually end those talks by reminding the students that the samples we are collecting will be arriving back on Earth in the 2030s, that by pursuing a career in science and engineering, they can help answer the questions that we are currently waiting to answer. As we inspire the next generation of researchers, I imagine all the wonderful things that we will be able to accomplish and all the big questions we will be able to answer from these samples. I would be happy to answer any questions you have.
Dr. Beagle, thank you very much. And our grand finale, Dr. Bozak, floor is yours.
Chairman Meyer, Ranking Member Babin, and members of the subcommittee, thank you so much for inviting us to share our delight with this mission so far. And it is great just to see you all excited about Mars science. Because I think we're all excited because we are just at the beginning of a truly exciting time with the landing of the Perseverance rover in Jezero crater that Bethany showed. We'll be able to identify and collect samples of rocks, soils, and minerals from this known location on Mars. And the return of these samples to Earth is likely to transform our views of planetary evolution, climate, habitability, and even the origin of life. And this is an ambitious endeavor and one that will inspire the children of today to learn more about science and technology. Why it's ambitious? Well, we are bringing samples back from Mars. But not only that, but for the first time, we really will dare to ask the question of whether these samples contain something that may have been life. We are looking for life on other planets. And this is a very old question. For millennia, in fact, people have wondered whether there is life outside of Earth and how and when life began, what conditions are necessary to get life started. And so far, Earth is the only known planet with life. Scientists like myself find the earliest signs of life in some of the oldest sedimentary rocks on Earth. They're 3.5 billion years old. However, if you ask us how life began, we'll start hemming and hawing, and that's simply because we don't have the answer to that. Nobody knows. So to answer this, some scientists are trying to synthesize organic molecules that are present in all living cells and even make protocells in test tubes. Other scientists look at old rocks on Earth, but there are few preserved rocks on Earth that are old enough to tell us what our planet even looked like more than 3.5 billion years ago. And this is where Mars comes in. It has this amazing history. The Mars 2020 mission will collect more than 30 pencil-sized samples of rocks and soils in and outside of Jezero crater. And many of these rocks are older than 3.5 billion years. They attest to a warmer Mars that contained liquid water at the surface. If those conditions lasted long enough, they may have supported microbial life. So if we sample these rocks and analyze them on Earth, we really can open the window into a time that we currently know little about. So the samples from Mars have to be returned to Earth to be analyzed. We heard that already from Michael and Luther. The analysis to look for life in rocks, one has to cut them, one needs to make thin slices of them to look through them, one needs the best microscopes because we are looking for microbial life. Everything that has to be microbial. We also need other types of instruments to characterize the organic molecules that may be present and all sorts of other chemicals, even to tell exactly how old those rocks are. We need different types of instruments. We simply cannot miniaturize all that and fit that many instruments on a single rover. So once the samples come back, scientists will analyze them for decades, just like they're still doing with the rocks brought back from the moon by Apollo. And this was more than 50 years ago. The analysis of Martian samples will determine how and when different rocks formed or were altered by water, how and when the climate on Mars changed, and how to best prepare for human exploration on Mars. Some of the rocks might even contain organic matter or remains of former microbial cells. So all in all, the samples brought back from Mars have the potential to revolutionize our understanding of whether life was ever present on Mars. And even if you don't find life, I get this question a lot, so what if you don't find life? By looking at samples from early Mars, we can always learn a lot more about organic molecules and processes that preceded life on Earth because of all this great age of these samples. And some of the findings that arise from the samples may even challenge our current interpretations of what life is or how to detect it. A lot of the findings, if not all of the findings, will also motivate future missions to Mars. All this is great, but it's much greater than science. Since Perseverance landed, I've talked to hundreds of people or through radio shows and to schools, and I've received dozens of emails from just random people from all over the world and from all walks of life. And what these emails and this personal communication has shown me is that Mars exploration inspires people to engage with science and technology because it resonates with people's innate curiosity about themselves and our own place in the universe. And that curiosity in turn inspires us to do more. So I will be happy to answer any of the questions you may have.
Thank you, Dr. Bozak, very much. Fascinating opening comments. I'll recognize myself now for 5 minutes for questions. And Dr. Bozak, I'm going to come right back to you. So you're our geo whatever.
Geo whatever.
Geo whatever. Is the geology on Mars as varied as it is on Earth in terms of the elements themselves? You know, the potassium and carbon and zinc and you know, basically are the building blocks there as they would be on Earth?
Mars is a rocky planet, and this is one of the reasons why we are so fascinated by it. It is so close to Earth. It is really the closest planet to Earth. And it does consist, because it's rocky, these rocks are the source of all the elements we need. Well, a lot of the elements such as iron and calcium, all of the stuff that goes into bones and so on. So Mars has all of that. Now, the question of organics is a very interesting one. So carbon, nitrogen, oxygen, because rocky planets get these elements probably, and water as well, later in their history, still really, really early in the big scheme of things. But later in the history, and we think a lot of that material came from asteroids and comets, so from elsewhere in the solar system. And so by looking at these old rocks from Mars, this is one of the actually aspects of the mission and the return samples that is most exciting to me. We can start asking how much delivery was taking place. What is this background delivery of these compounds that are needed for life to rocky planets?
Thank you very much. And Dr. Meyer, you've been a specialist in astrobiology. Dr. Bozak earlier talked about, life evolving, trying to understand. Was the organic soup ever there, the lightning? Our limited understanding of how life evolved on Earth, could those conditions have been on Mars also?
Well, so that's actually one of the big questions. We think so, and that's half the reason why we're looking. But in all honesty, there's three major theories about how life got started on this planet, and we don't have a very good evidence to point one way or the other. And as Tanja talked about, the rocks on Mars, over 50% of the rocks on the surface are ancient. And here on Earth, they're few and far between, and they've been worked over. So evidence of exactly what was going on in the first billion years of terrestrial planet history, we don't have a very good record on Earth, and we think the record is on Mars. So whether or not we had the organic soup and lightning that caused life, or whether or not it was a hydrothermal vent, these are things that going to Mars can help us sort out.
Thank you very much. And Dr. Ellman, as our planetary scientist, we saw Elon Musk last week, the week before, talk about terraforming Mars. Is there enough water there to justify that? Can you see transforming the Mars environment sufficient for human life?
Well, I will say that the premise is correct in that Mars is the closest potentially habitable world, right? It is really the only one that has an atmosphere today, as well as abundant water resources. We know right now, they're in solid ice. So the question is, does the ice melt now naturally, right? That's a question Perseverance won't answer yet. Is there modern life that could be associated with this ice? I think I'd like to actually answer that before we send humans, but regardless, terraforming Mars would be hard. So I'm a planetary science, but I'm also a geologist by training. And I know that to make a planetary atmosphere thick for humans to breathe, you have to figure out some way to produce oxygen. You have to figure out some way to thicken the atmosphere so that it's warm enough. And on Mars, lots of the water and the carbon dioxide are actually trapped in rocks. So hard to release. I would love to send humans to Mars to explore. Changing the whole planetary climate, maybe not so much.
Yeah, I love the optimism in any case. Is there enough gravity there to hold an atmosphere?
There is, and Mars has an atmosphere today. It's a little less than 1% of the thickness of Earth's atmosphere. It's 96% carbon dioxide, but very, very, very thin.
That's great, thank you. Dr. Beagle, very quickly, do we have enough talent in the pipeline? We worry so much about STEM education and the like.
We do. We have some very, I look at the postdocs and graduate students that are working on Perseverance and have worked on the development of Perseverance. And there's some outstanding talent coming up and even more on the way as we continue to push people into science, well, not push people, but inspire people to go into science and technology. We have a great pool to draw from.
That's very encouraging to hear. Let me now recognize my friend, Dr. Babin, for his 5 minutes of questions.
Absolutely fascinating. I just want to thank all four of you for being here and giving us your testimony. And Mr. Chairman, thank you for having this. I guess my first question would be for Dr. Bosak. I proudly represent the Johnson Space Center here in Houston, where many brilliant, hardworking government employees and contractors also work here. JSC is at the center, presently charged with curation of extraterrestrial samples, and is home to the Astro Materials Acquisition and Curation Office. JSC has experience curating samples from the Apollo moon landings, meteorites, cosmic dust, and the Genesis, Stardust, and Hayabusa missions, and will process samples from the OSIRIS-REx mission. The Mars Perseverance mission is gathering and storing samples for an eventual Mars sample return mission, fascinating, which is still in the planning phase. From your perspective as the co-lead on return sample science for the Perseverance rover mission, does NASA plan to store and curate Mars sample returns at Johnson? And what impediments are there to using JSC's Astromaterials Acquisition and Curation Office and the unique capabilities that JSC possesses? Because I would like to do everything that I possibly can to eliminate whatever impediments those might be.
Unfortunately, I'm not, well, not unfortunately, we are really responsible, the team of Mars 2020 mission, the Perseverance rover mission is responsible for recognizing, identifying, and collecting the best samples. And the plans for curation, storage, later allocation are all under development by the Mars sample return program. So I think the plans are being developed not by necessarily the team members of Mars 2020. I think Michael can speak more to that.
Okay. Dr. Meyer, can you speak to that?
Yeah, I mean, Johnson is long recognized for their expertise in astromaterials, and I think they do a fantastic job. And we are targeting Johnson to be the implementation lead for the samples that come back from Mars. Where the facility is actually located, it hasn't been determined yet. And part of that is just what other factors are coming into play. And as an example, we're right now on an international group, competitively selected, trying to work out what the requirements are for the facility. Because as you know, the Mars samples are unique and they have some challenges of not only keeping them pristine and doing the best science that you can on them, but also keeping them contained while you're trying to do the science, at least initially. And so we're going to, we would like to open that up and have, when we figure out really what the requirements are and what our capabilities are in terms of the facility that we can do, Johnson will lead that effort in terms of determining where the actual facility is.
Okay, thank you. And I guess your testimony also highlights how Perseverance is paving the way for future crewed missions to Mars by demonstrating oxygen production with the MOXIE instrument and the use of terrain relative navigation that you have mentioned. Can you speak to how terrain relative navigation will also assist future Artemis missions to the moon and how it could be incorporated into human landers?
Yeah, well, certainly the issue with particularly with Mars and in the moon is that there's a time delay between when something happens and when people on Earth actually get to see it. So when you're trying to pick precise landing, you want to land next to the equipment you left, that you put there for your humans to go to, or resources that are available. You need precision landing, and terrain relative navigation has shown us that we can do it autonomously. And so for that, we know that we can put things on the surface of another planetary body and put humans right next to them so they can use them.
Thank you very much. And now for Dr. Beagle, is the Perseverance rover looking for signs of life or signs of ancient life? If NASA is only searching for signs of ancient life, is this because the estimates are too complex or perhaps too costly to search for extant life, or because NASA doesn't believe that Mars is capable of harboring life anymore? Understanding that you may be a little biased as a Mars researcher, how should this information play into considerations of whether to continue exploring Mars or to focus more on Venus, Europa, Ganymede, Titan, or other celestial bodies?
So we're looking for signs of ancient life because we simply don't believe that Mars is habitable, at least in the upper few centimeters today. But as Dr. Ellman has pointed out, that Mars is the most Earth-like planet. And if life started there, we would assume that life would, if we find that signs of ancient life, we could tie it back to what started life on the Earth. And Europe and Ganymede may have had different origins of life if it started there at all. So while we could find it if it was there, we don't expect that any extant life to be present.
Okay. I have, did somebody want to say something?
If I could just briefly add, I think wanted to emphasize, Dr. Beagle noted that it's the upper centimeters that we don't think are habitable. But once you get down a meter or maybe few, right, it gets a lot better. You're out of the radiation. You might be near some ice or water. So that's the place to look on Mars.
Well, you know what? I didn't get a chance to ask you a question, Dr. Ellman, but thank you very much for that answer. And I could go on for the next 1 hour at least, but I'll have to yield back, Mr. Chairman. Thank you.
And Dr. Babin, I think we're going to do at least a second round because our curiosity is large.
Absolutely.
And with that, I'd love to introduce perhaps the greatest enthusiast for Mars exploration in the U.S. Congress, the author of the Mars 2033 bumper sticker that many of us have, Congressman Perlmutter.
And I'm sorry I don't have that today because I'm in California, but I got to tell a story. So Dr. Bozak, your question or your comment about the enthusiasm of people, reaching out to you. So I chair a different committee on financial services, the banking subcommittee, and I was getting interviewed by the Wall Street Journal just as Perseverance was landing a month or two ago, whenever it was. And I couldn't talk about banking. All I could talk about with this guy from the Wall Street Journal was the Perseverance landing. And it's because I was so excited about it. And I am excited about the efforts and the successes that you've had so far. And Dr. Babin, a lot of times you can't have success without, a few trials and errors. And we've had those too. But this one seems to be, each time you try something, ingenuity, it took you, reprogramming it a little bit before it could take off. The cameras, Dr. Beagle, seem to be working fantastic. We haven't quite tried the drilling yet, I don't think. But, you're taking these one step at a time. So I want to talk about Moxie and I want to talk about ingenuity if I could. And so explain to me the process, what's going on with Moxie as we're figuring out how to create oxygen on this planet, which will benefit us, in many different ways. And I just open all of these questions to all the panelists. So jump in as you choose, Dr. Beagle.
So I can explain what's going on with Moxie. And Moxie did a run the other night where they take CO2 out of the atmosphere and they turn that CO2 into breathable oxygen or oxygen that can be used for rocket fuel. They run overnight. It's a wonderful instrument, and they created enough that you could breathe on Mars for 10 minutes, which doesn't sound like a lot, but really it's the start of that whole process. And it's a fascinating instrument.
Anybody else want to talk about Moxie, and then we'll get to ingenuity? Okay.
If it's okay, what I would like to mention is that the way it does is it splits the molecule. So it strips the two oxygens off of the carbon, and that's how it's generating the oxygen. So it's kind of a neat process. It takes a catalytic converter, but it's a test, and the volume depends on how big of a thing you want to use.
Great, the old catalytic converter. That's amazing. So, Dr. Meyer, do you see this as sort of a precursor of some kind of bigger system that would then, enable so I am a big proponent of human space exploration and hope to see our astronauts on Mars by 2033. And I wish I had my bumper sticker for you, but I don't. Do you see this as something that we could put together to really provide oxygen for our astronauts or for fuel? I mean, a massive kind of approach to this.
So how I see the real advantage is that you can put a system like Moxie onto the surface of Mars and have it operating for years. and then send humans, or then send your return spacecraft, and you can make use of that oxygen that has been generated. You know, one of the things to keep in mind is that rocket fuel is an oxidant and a reductant. So like something like methane or ethanol, and then the oxygen. Well, the oxygen is actually the heavier part. So this goes a long way in making getting to the surface of Mars with something you can return it. If you make most of the mass of your fuel on the planet itself, it's a huge advantage.
Great. To the geologists, how are you going to use ingenuity to help you explore a little bit of the geology up there?
I guess I'll start and then hand it over to Professor Bozak. So, Ingenuity is a technology demonstration. It wasn't even originally part of the mission, but I think that is part of the reason that we explore, and that is part of the reason the US space program is so outstanding, is that we dare to do audacious things like fly a helicopter on another planet. Like, wow. And you know what? We figured out how to do it. It worked. And so Ingenuity is going to, on its final flight, scout out some of the terrain around us, we hope, getting a closer view than what we have from orbit. But what is, I think, super important is how it paves the way for future exploration technologies. There are already folks at JPL who are talking about, well, what if instead of carrying a tiny little 500-gram cell phone camera, could we put 5 kilograms of science payload on there so we could fly down the canyons of Mars from spot to spot, taking images, making chemical measurements? So I think what's important about Ingenuity is it's paving the path for future exploration.
Thank you very much. My time has expired. Mr. Chairman, I love this stuff. I yield back.
That is obvious, Congressman Promoter. And we're all so fortunate. Let me now recognize the ranking member of the full committee, the past chairman of the Science Committee, Congressman Frank Lucas.
Thank you, Mr. Chairman, and I address my questions to the panels in general. This committee's always promoted a balanced portfolio at NASA, and we've worked very hard by the informed nature of the National Academy's decadal studies. Our committee's always been very supportive of planetary science missions throughout the solar system. Given the number of Mars missions during the last decade, how would you recommend we balance the planetary science portfolio in future years? Anyone's willing to touch the wire, I'm happy to listen.
Well, sure. I'll touch the hot wire. So what's most important is that, scientists, we need to get together and prioritize our science and then communicate those messages to Congress, to the president. And so we're in the process of doing that right now through the National Academy's Planetary Decadal Survey process. So over the last year and a half, we've been trying to hash out that question, arguing amongst ourselves, well, what is the right balance between outer solar system, inner solar system, small missions, big missions? I think the answer is we need a Mars exploration program because Mars is unique, Mars is special. Mars sample return is an enormous investment, but it pays it back. It pays it back in terms of proving how we can come and then go and then bring back. We would want to do that before humans, and the science return, as Professor Bozak said, will be amazing. So we need to have that balance, and I can say the Planetary Decadal Survey looks forward to communicating to Congress its relative prioritizations.
Absolutely. Perseverance has already demonstrated multiple. Please.
Oh, sorry. I'll also add that we do the other missions as well. So there is a balance. We're working on the orbiter mission, right, on Europa flyby mission right now, Europa Clipper, and there is the balance. I think most people in the community think there is a decent balance.
I would just like to add one thought, if that's okay. It's balancing the science of planetary sciences, not necessarily equal number of targets in terms of missions. And in some ways, Mars has an advantage because of the amount of information that we can learn from exploring Mars, and the short, let's say, the not so long time to get there and get the information back. So it has a little bit of an advantage. So I don't feel so bad that we've had so many missions to Mars, because they have really returned fantastic amount of data. And I don't envy Bethany's job on the decadal to helping sort out what those priorities are.
Absolutely. Perseverance has already demonstrated multiple technologies that will assist in the future human exploration of the moon and Mars. And to help Mr. Perlmutter achieve all those goals, what are some of the examples of technology demonstrations on future planetary missions, which will further assist human exploration throughout the entire solar system? Again, I'm trying to help Mr. Perlmutter.
I'll take a quick crack at that, and hopefully my other fellow witnesses will chime in. But there are things that will really help human exploration that we actually haven't demonstrated yet, and that is, for instance, rendezvousing in space with your spacecraft, testing out operations. So one of the challenges are, I used to do field work, and there's a world of difference between doing something where you're 3 days away from help, like a hospital or food sources, compared to multiple years. And so I think one of the key parts of Gateway and the Artemis program is, in fact, testing out your operations and your housing for the astronauts to be reliable on the long term.
I would also add that there's an aspect of autonomy that we don't talk enough about. There's a couple of versions of autonomy. One is the rover drives itself, but there's also the idea that the rover can figure out how it's working and how it's functioning and what its basic mechanical state is. As we develop more and more autonomy for the rover to figure out what's going on, that helps in human spacecraft, because you will have the human rovers and equipment and things like that really be able to understand how well it's functioning, whether or not it's about to break down, which is something that would be very valuable for human missions.
My time's expired. I wish to thank the panel for those insights and yield back to the chairman.
Thank you, Congressman Lucas. And I recognize the congressman from Greater New Jersey, or leaders on education and labor, Congressman Norcross.
Thank you, Chairman. Appreciate it. And the people who are on this call, you can just see the smiles, because it's things that we believe passionately about. As a young man, the Mercury, Gemini, I was one of those kids that got NASA tech briefs when they used to be put out on paper and had no idea what I was looking at. But it's that sort of driving force that keeps me and so many involved, because it's about what we're learning. I want to talk about private investment. If you Google private space, you'll get 25 different companies. So I sort of split those into two categories: those who are facilitating different components, whether it's the rocket or the instruments. The other side of that is private investment into space. What do you think drives the private investment for the future? And I would assume this is way in the future, to either Mars, to an asteroid, or others. What will drive them that there is a payback? And when do you think that would happen? I know it's a wide open question, but at some point you do all the work and somebody comes in and takes the profit out of it. But where do you think that enters, and where do you think it would be? And that's for all three. Love to hear that.
I guess I'll start us off. So there's, private industry has always played a huge part. So many of the procurements for our rovers and instruments are from private companies. So big role. I think what you're poking at, though, is that role seems to be changing a little bit. And I think it's driven by the increasing access to space, driven by lower launch costs, and a number of companies are competing in that arena, just lowering the cost of access. The other thing that's happening is with small sats and with commercial technology in orbit, there are many more entrants into this field, many more private companies, small private companies building components. So I think the motivation is largely profit, that we see a market in space. And I think the challenges for us as planetary scientists is to think about how to extend that market to enable more exploration and more activity. It's happening at the moon with the commercial lunar space flight program. The CLIPS program. I want to think about, can it be extended to Mars if we, like, for example, regularize the delivery or set up, comm infrastructure contracts to provide communications from rovers and landers back. These are things industry could do. So we have to think about what's the right role, what's the right contracting vehicles to have, shared risk, for example, in some of the development, and how do we incentivize that? Some people want to go anyway, right? Just to go, like Elon Musk is an example, right? Others, they see the market. And so we need to think about how to incentivize that to enable more exploration.
If I could, just to sort of narrow the focus, I understand plenty of investment to getting things out there, the Rocket Lab, SpaceX, the list goes on. Moving beyond what we already know is a commercial space around our planet, the moon, Mars, or others, what's going to drive them into that next spot? How long did it take for really get private investment around our own planet from when we started this game, right? 40 years. Where do we think this is going, and what would drive them to go to a moon or back to Mars? What do you see as a reason for them to go there?
I will say that I'll just say real quick that there is a cadre of companies that are looking into asteroid mining, and that is something that it seems to be picking up speed. So that would be the first commercial aspect of return on investment that potentially would be made one day. But beyond that, I will defer to Dr. Meyer.
I am certainly not the expert, and this is highly speculative, but I remember hearing a talk about 15 years ago at a Committee on Space Research assembly. And essentially the person said, we will be at Mars with humans sustainably when it becomes when you're able to do it for tourism. And when I heard that, I thought the person was nuts. But then the more I thought about it, and the more I had to answer my cell phone, the more I thought, what a great pleasure to be where you get someplace where you're so far away that you can't have regular conversations with everybody else who wants to talk to you, but you can actually take a vacation and you can be someplace entirely exotic for an extended period of time. And it makes more sense to me now.
Can I suggest a Codell? Maybe to Mars? Mr. Chairman, thank you. I yield back.
We'll ask the full chairman and the ranking member for permission to schedule that Codell. Thank you, Mr. Norcross. I now recognize Congressman known for many reasons, but best known as the Congressman from Cape Canaveral, Mr. Posey.
Thank you, Chairman Meyer and Vice Chairman Babin for holding this very, very interesting hearing. Dr. Meyer, you mentioned that just getting a spacecraft to launch during the pandemic was no easy feat, and I assume, especially considering a 2-year window. Can you describe some of the challenges that COVID-19 posed to launching on time, and how NASA and ULA were able to work together to overcome those challenges?
Yeah, I mean, this is something that with only be able to talk for 5 minutes in the beginning is something that I wasn't able to delve into. And so thank you very much for the question. I think it was a tremendous heroic effort. And as you mentioned, just getting a spacecraft to the launch pad on time to meet the planetary window, that's a huge challenge. And as we know, in the past, we don't always make it. And this time, having a COVID show up basically in the middle of what's called ATLO, assembly testing and launch operations, it was tremendous. And so one of the things that really struck me was the whole operation team down in Florida had to basically form their own COVID bubble. So they had to be with each other all the time, which is maybe not necessarily a bad thing, but they had to self-isolate. in preparation to going to Florida, and then while they're at Florida, and then how did you do some of the rotation? It was an extreme challenge because that was the only way that you could actually get together and work on the equipment that you have to send to another planet. Otherwise, you can't do it all by Zoom.
Well, thanks. That's a great answer. In your conclusion, you state NASA's Mars exploration program continues to lead the world in learning about Mars and developing technology that allows us to delve even deeper into the secrets of the planet. And I'm just wondering, with this being the 9th mission to have a U.S. spacecraft successfully land on Mars, what are some of the secrets that might be hopeful? You know?
Well, this is a public meeting. Do you want me to reveal those secrets?
Well, kind of swag them. I mean, you know,
yeah.
What do some people hope that we'll find on, you know, on the best view of things? What can we discover?
Oh, you mean what we may find on Mars, or are you talking about what the challenge, the sort of the how have we been successful? I'm kind of.
Yeah, I think you mentioned, you know, that as we delve deeper into the secrets of the red planet, you know, with each mission, just, you know, what might we be looking forward to finding out about Mars?
So, yeah, so, okay. Well, as been mentioned, Mars is very similar to Earth, and some aspects to it that I think are absolutely fascinating. One of them is it's gone through huge transformations in its climate. And this happens on multiple time scales. But the record is what the planet actually did is there. And so in some ways we can look at those rocks and determine, well, what happens when you increase the atmospheric pressure by twice as much or 10 times as much, or, you know, even as much as Earth. You can look at how the tilt of the planet has varied the climate. It really helps you to test your climate models on another planet where the planet itself has done the testing for you. It's done the experiments. And so then you get a much better idea of how a planet behaves with its atmosphere when conditions change. And it's kind of simple in terms of, for instance, on Earth, while we're increasing the CO2 in our atmosphere, and we have models that kind of tell us what we think is going to happen, Mars has some great examples of extreme variability that will tell us and give us a much better idea of how that's gone back and forth. And real quick, I think this has already been mentioned, but certainly should never be forgotten. If life got started on Mars, there's still places where we think that life could be there today. And that's going to be a real challenge. And let's say the last refuge that we can think of as scientists is in the deep subsurface and where we think there are potential aquifers. So that's one of those almost a horizon goal in terms of looking for life on Mars.
Well, that's super interesting, and I thank you for explaining that to us. And I see my time has expired, so I yield back, Mr. Chairman.
Thank you, Mr. Bozak, very much. Now recognize the gentleman from Florida, Governor Christ.
Hello, Mr. Chairman. How are you today?
Excellent.
Great, great. Is it my turn? I'm sorry, I couldn't hear you for a minute.
Yes, it is your turn.
Thank you. Thank you so much. And I want to thank the witnesses for being with us today. Dr. Bosak, can you discuss what you are trying to find on Mars that would indicate microbial life and how you will know definitively if life does exist on Mars? Please.
Yes, so we are looking for past life. We are looking for life as it may have looked like 3.5 billion years ago or even earlier. So we are not looking for current life. And based on—
You're looking for dead life. So
dead life, exactly. So what we are looking for are fossils, fingerprints of some fossil life. And I can actually show you some examples of rocks that would tell me, just based on their shapes, that there must have been some life there. And that's probably the holy grail of what we can hope for by this mission, just to see something in the field. But because we are looking for life that really, from everything we know about life on Earth, must have been microbial, we will have to bring samples back, and we will have to analyze these samples with, it won't be one person who looks at one sample with one instrument and says, oh, I think I see an outline of a cell, some former microbial cell. And so we are talking something that is microscopic. But there'll be another team that has to look at that outline and say, yes, I see organic carbon in there. And then there'll be another team looking at the same outline and saying, yes, we see some concentrations of elements that usually go with carbon in living organisms. And then someone else will have to measure the shapes and sizes of all these features and say, oh yeah, they really are consistent. And we cannot think of any processes that can create that. It can be just oil bubbles or something, some asteroid delivered some material. So there'll be a lot of different tests that will have to go in, because it's an extraordinary claim. And before we make those kinds of announcements, we will have to really make as certain, based on the knowledge of the time, that this could be life. We will have to discount everything else.
Wonderful, thank you. Dr. Ellman, you note in your testimony that the rock record on Mars extends much further back in time than what is preserved here on Earth. Based on what we know of Mars right now, do you think it's possible that we could find signs of life on Mars that are older than the first signs of life on Earth?
That's actually a great question. The oldest life that people sort of agree upon on Earth in the fossil record is about 3.5 billion years old. There are hints of earlier life, maybe as far as 3.8, but the problem with our Earth is that, one, we have tectonic plates that deform the rocks, that heat them, that mess up the textures. And also, frankly, new Earth life eats organics from old life. So our life itself is destroying the record of past life on Earth. So yes, I do think it is possible that it looks like all the conditions existed on Mars 3.5 billion years ago to create habitable environments. The record is much more pristine though, because it's sort of captured frozen in time over 50% of the surface. So we have lakes, rivers, aquifers like underground in Florida, and hydrothermal systems, all of which are different types of environments to look for life.
Wonderful. Dr. Meyer, when talking about the possibility of life on other planets, we hear a lot about liquid water and looking for signs the conditions are right for water to exist. What are some other known requirements for life as we know it to exist on other planets?
It is broader than water because, with water, at least we find that consistent and we don't have to argue about it with life here on Earth and what we think life is capable, what the potential for life is in our solar system. But yeah, there are certain major things that should also be there. One of them is of course, the right elements: carbon, hydrogen, nitrogen, phosphorus, and sulfur. Those are the things that we're all made out of. That's what everything that's alive on Earth is made out of. So you would hope you'd have those. You probably want certain compounds. You may want some trace elements because they're important for enzymes to work and that sort of thing. The other is, in fact, energy. And this may be a more challenging one to look for extraterrestrial life, because if you don't have enough, you can't do anything. If you have too much, the energy is too much and it destroys what complexity is liable to evolve. So those other things are sort of other things you look for. And in fact, one of the great things that Curiosity did within the first year of its mission is, in fact, it found everything that we can think of that are required for life. And that's why we can now say, yes, verily, at least early Mars could have supported life if it ever got started there, because it has all the right ingredients.
Great. Thank you, Doctor. And Mr. Chairman, I'll yield back. My time has expired. Thank you.
Thank you, Governor, very much. And we're going to move to a second round for anyone who's brave enough to hang in there. But I completely understand, as busy as our schedules are right now, if members have to go off to other things. So let me begin. And by the way, thank you, Dr. Babin, for co-chairing this with me. First, I want to apologize for our panelists for having Andy Weir appear before the Space Subcommittee before you. You know, and we actually packed the room with press. But anyway, that's just on sample return, and maybe this is a question for Dr. Beagle. Are we dependent on the human space flight to Mars to retrieve it, or can it be retrieved in the meantime?
That's a great question, and the answer is that we can retrieve it in the meantime. There is a series of missions that are proposed that Dr. Meyer can talk more about that will go pick up the samples that we're collecting and eventually bring them back in the 2030 timeframe. And all that can be done robotically.
So 2030, so a couple of years ahead of the Perlmutter schedule for human spaceflight to Mars.
Yes.
Okay, excellent, great. Let me ask a deep existential question for you guys. Of the four of you, and I rarely ask for the whole panel a question, but I'd love to know where each of you are on your belief that there is other life in the universe. That life seems to be so unique and consciousness itself so unique. Dr. Bozak, can I start with you?
Certainly. I will tell you this. One of my favorite, if not the favorite, science fiction book is His Master's Voice by Stanislaw Lem. He was brilliant. And it is not so much about whether there's life, but about the people's need to look for signs of life and interpret signals and keep interpreting signals. The whole book is about this whole field of science and people being fascinated by tiny signal they captured from some star and arguing about whether it's a signal at all. So I think part of the excitement, and I think this consciousness that makes us unique. I think the search makes us unique. It really makes us something bigger than just, microbes converting energy to live. But then again, if I start thinking about life, I think mostly, I'm a microbiologist really. So I think of life mostly as microbes. And that probably doesn't have too much consciousness, yet it can be really easily spread. And in fact, even the ancient Greeks talked about seeds that could travel from stars and planets to other planets. And this is the really cool thing about this mission and the sample return, because we can actually test some of that. There is a strong idea that maybe life even started on Mars and then was transferred to Earth early on. And we can now start playing with these ideas. We can look at these samples and see how similar, if anything, we find how similar it is.
Well, thank you for the book recommendation.
It's great.
To begin with. Dr. Ellman, is there other life in the universe? I mean, your leap. I know, just what do you think?
This is one of the reasons we explore. I think there is, and I think many people think it would be strange that in the vastness of the universe with billions of stars, each of which have many planets, that we are the only ones. But I agree with Professor Bozak that it's the search that matters. It's the search that's inspiring. And, just even thinking about our own solar system, the question was asked earlier about the portfolio of exploration and balance. We now have the technical capability to look for life on Mars, on Europa, on Enceladus, on Venus. We should do it because this is an inspiring journey that really will inspire the whole country to do hard things. And let's start the questions, the life questions in our own solar system where we can access the planets while we keep using telescopes to look beyond.
Thank you very much. Dr. Meyer, I guess since you call yourself an astrobiologist, that may be implicit in your title, but what do you think?
Yeah. That's a big yes. I mean, as Bethany says, there's like 100 billion stars in a galaxy, and there's 100 billion galaxies. It would be absolutely spectacularly amazing and hard to believe if there wasn't life out in the universe. The real question is, how common is it? Because if it's on the other side of the universe, how likely it is that you'd ever find it or notice it. And so the real question is commonality. And as Bethany says, in our own solar system, we see multiple places that have real potential. And we are the first generation of people on this planet that can actually do experiments, can actually go and look and answer the question how common life is in the universe.
That's very cool. I'm going to use my extraordinary powers chair to let myself go over because I want to hear Dr. Beagle's ideas also.
So I agree with Dr. Meyer and Dr. Ellman and Dr. Bozak that life is, the odds of life not existing elsewhere in the universe are very slim. The questions we ask ourselves a lot is that how is there more than just single-celled organisms? It took a long time on Earth before life evolved from the single-celled organism to multi-celled organisms, and that's the question we continue to ask and ponder, which is a much more difficult question because it involves understanding the evolution of life on different planets that you have no idea what the conditions are like, and that's the question that we really are trying to sink our teeth into.
Thank you very much for and I ask this because my favorite recent book is Max Tegmark's The Mathematical Universe, who finishes with a strong argument against there being other life. And he says in any room full of scientists, he'll ask who believes in life elsewhere in the universe, and every hand will go up, and then he argues against it. But I'm not going to try to recreate the argument, but it is interesting. However, I will like to recreate the congressman from Denver, Mr. Perlmutter, for his questions.
Thanks, Mr. Chair. Yeah, and he sent me that book, and I'm trying to wade through it. It's a pretty heavy math book, but he's trying to educate us as part of this subcommittee. So, Dr. Meyer, let me start with you. When I was talking to Dr. Ehlmann about ingenuity, she said it was an audacious addition to the project. So how, and for the others, how do you get your experiments? You know, once you've decided we're going to send another rover up to Mars, I mean, how does Dr. Bozak get her experiment on the trip? So let me start with you, and then I'd like to hear from their side how they managed to get their experiments as part of the whole process.
Yeah, well, I'll put it this way. It's quite a gauntlet in terms of what's needed. But as we've done for Curiosity, and we also did for Perseverance, we put a call out that says, we're going to send a mission to Mars. This is what the goal is. Send us your proposal for an instrument, and we'll see how it all fits together. And so it very much is open competition for people to propose whatever they think is applicable to the goal, right? And very rigorous competition. It's actually very hard to go through the whole process, and then you have to choose. You have to narrow it down to those things that will fit on the mission from all the excellent proposals that you receive. And then there's a little bit of a give and take where you don't want to send two of the same instrument. You want to make sure they complement each other. You want to make sure one instrument doesn't use all the resources on the mission. So there's a little bit of making sure they fit well together. But the real process is individuals, obviously experience and having a whole team behind them, proposing what they think would be the best instrument, and then the whole review process to select that. And that's been extremely successful so far.
Great. Dr. Bozak, how did you get involved with this project?
I answered one of these proposal calls. When all the instruments already had been selected and really advanced in the works to get on the rover, there was a proposal call by the Mars program to select participating sample scientists. And they were looking for people who actually work on samples in laboratories, because they wanted to ensure that people think about how to collect a sample, how to orient a sample. And there is a diverse team of us who were selected. So we wrote proposals about what we could do with these samples and how we would take notes to document and tell people why we selected certain samples.
Great. Dr. Beagle, how did SHERLOC become part of this?
It's a pretty simple process. Back in the mid 90s, we started thinking about ideas on how to send something to Mars to look for life. You write a proposal, you write more proposal, you write another proposal. You have to go in and do the scientific rationale behind what measurement you're going to do. At the same time, you're doing the engineering to show that you can actually do it. So a lot of instruments that fail on one of those two things because it's a very complex environment scientifically to make a measurement, and it's a very complex environment from a temperature, pressure, radiation, and everything else that you have to show vibrations, that you have to get your technology to work. You write a bunch of proposals, you write a bunch of papers, you get scientific buy-in. And then in 2012, we knew that there was going to be an announcement of opportunity. We spent a year writing the proposal. We submitted the proposal. Proposal got accepted. There were 58 different concepts that went into that call, and we were one of 7 that got selected. And then the fun really begins where you actually have to build your instrument that's the size of a room down to the size of a shoebox and show that it works. It's a fun process.
Well, it sounds, starting in the 90s, it sounded like you were able to perfect it over a period of time. So thank you. Dr. Ellman, what about you?
I guess I'll talk about something that people don't always talk about, which is kind of the failure aspect of instrument proposals, or not failures, but lack of selection. So, I'm privileged to be part of 2 extraordinary instruments, one led by Dr. Beagle, part of his team, and then Jim Bell at Arizona State, part of his team. I also led a team that proposed an instrument, one of the 58, to the rover. We ranked category 1, which is as high as you can possibly rank. But in the end, we weren't selected. Reasons of balance, but this is where as scientists we compete and then we collaborate and we do both simultaneously, and that's what brings the best ideas to the forefront. I've gone through this process again, a different mission, different competition, different call, one of NASA's small sat competitions, and I'm the principal investigator of Lunar Trailblazer, a small satellite going to the moon that will map its water. So it's a process. Sometimes you win, sometimes you don't, but you keep going forward to do the best science and bring the best instruments and missions to light.
Thank you very much. I yield back, Mr. Chair.
Congressman Perlmutter, thank you so much. I love serving on this committee with you. And this brings our hearing to a close, but I do have one final question is, after Mars, Europa? What do you think?
Europa, for sure. Europa Clipper mission.
Okay.
Enceladus would be great too. Venus, all sorts of good things.
But Europa we could actually land on, right?
Yeah.
And water. And
yeah. One of the missions, I think the next mission to actually look for extant life would, as Bethany, Dr. Ellman pointed out earlier, is drilling, is getting underneath the surface of Mars and or Europa and or Enceladus to that protected environment where there's liquid water on Europa and Enceladus, and where there might be aquifers on Mars. That would be the one thing I would advocate for.
Well, thank you all very much. This is definitely the most fun science committee hearing we've had since the folks who discovered gravitational waves came and spoke to us. And much more fun than Andy Weir, actually. So we hope we'll have you back. We look forward to all the progress you're going to make, not just on Perseverance and Mars sample return, but for humanity, because you really do inspire everything else that we do. So we're very, very grateful. And let me finish with the official closing. Before we bring this hearing to a close, I want to thank our witnesses, of course. The record will remain open for 2 weeks for additional statements from the members and for any additional questions the committee may ask of the witnesses. So with that, you're excused. Lunchtime. The hearing is now adjourned. And thank you very much.